focus of this lecture is optimization word problems, max-min word problems. In essence, you're given a task of optimizing, that is, maximizing or minimizing a particular entity such as area, cost, time, something of that nature. As an example, given certain parameters and certain constraints. The job is to write an equation including the entity to be optimized as related to the variables expressed. Once you get the equation, you will need to do the following. Take the derivative to determine the critical values, and then verify that the values you determine from the problem optimize the situation. The calculus is usually the easy part. Okay? Finding the equation will be the difficult part in working these problems. Let's look at some examples. Example 1. Find two positive numbers with a sum of 20 and a product that is the max. The first thing we have to ask ourselves is the following. What is it we wish to maximize? It's the product. So we must determine an equation that expresses product. So we're going to let P here, capital P, represent product. And we're going to let X be one number and Y be the other number. Therefore, our equation is that P is equal to X times Y. We have three variables here. In particular, we have P in terms of X and Y. We would like to have P in terms of either X or Y, but not both. So there is a piece of information we have not used yet, and that is the sum of the two numbers is 20. So we will write that. We'll express that as follows. X plus Y equals 20. Now we will solve for either X or Y. We here have solved for Y. Y is 20 minus X. You could have easily solved for X and said X is equal to 20 minus Y. Your choice. Okay, so we're going with Y is 20 minus X. Now what that means is that we're going to take our equation that we've developed, P equals X times Y, and in the place of Y, we're going to substitute 20 minus X. So we have P is equal to X times 20 minus X, and we need to find P prime. Now, you can, but I would suggest not using the product rule in this situation. It's much more cost effective to just go ahead and use the distributive property and multiply by X and rewrite P as P is equal to 20X minus X squared. We find P prime to be 20 minus 2X. We want to find the critical number, so we need to find where the first derivative equals 0. So we set it equal to 0 and solve, and we get X is equal to 10. Now, since we're told to find the numbers, if X is 10, we go back to our expression X plus Y equals 20, substitute X in 10 in for X and solve, and we get that Y is 20. So there are two numbers, 10 and 10. Okay. Now, to verify that this indeed is a max, we'll find the second derivative, which means take the derivative of this expression, and we get -2. -2 is always less than 0. So by the second derivative test, that tells us that P is a max. Now, this is a rather simple problem. A lot of people would look at this. In fact, more than a few people would look at this and say, why would you do this with calculus? And the answer is, we just simply want to acquaint you with a routine. Obviously, somebody that's never heard of calculus and derivatives would probably look at a problem like this, and the first thing they would do is they say, They would think two numbers that add together give you 20. 1 and 19. You multiply them, you get 19. 2 and 18. You multiply, you get 36. And they probably run through a few numbers and come rapidly to the conclusion that the two numbers are 10 and 10. But that's not the purpose of this example. This example is to get us started thinking, which is of a routine that we use. That is, find an equation. Usually we have too many variables and we have to rewrite the equation in terms of a single variable. And then we have to take the derivative and we have to set it equal to 0 to find our critical numbers. And then we have to use that answer to find any subsequent answers that might be asked for. And then we need to test to see if indeed we have found a max or min or whatever. So there's a routine to this. Example 2. You're given 1,200 yards of fencing material and you wish to enclose a rectangular area to serve as an animal pen. What dimensions must the rectangle have in order that the area enclosed is maximum? One of the nice things about a problem like this is you can make a drawing. You can have a figure to use for reference. And then you can label it and it helps get you through the problem. We've drawn a rectangle. We've identified this as W for width and this side L for length. You can use any letter you wish. That's what we've chosen here. Now, what is it we want to maximize? Area. So with relationship to a figure we see here, what is the area of this going to be? And it's going to be length times width. So we'll let A be area, and that means we'll write A is length times width. Now the perimeter of the rectangle, that is the fencing that'll go around, that's called the perimeter, is 1,200 yards. So that means we're going to have W plus L plus W plus L, or 2W plus 2L equals 1,200. Now, you do not have to do this, but we see that you can simplify this expression since everything is divisible by 2, and so we do that. And we have L plus W is 600. Now, 2 letters here. We'd like to get it in terms of 1 letter, so we need to either solve for L or solve for W. We've chosen to solve for L, but there again, you may have just as well solved for W. But since we have solved for L, we'll go to this expression, and in the place of L, we're going to put 600 minus W, which you see here, times the W. Again, we're not going to use the product rule. We're going to multiply this out. This is 600W minus W squared. Take the derivative, that's 600 minus 2W, set it equal to 0. W is 300 yards. If W is 300 yards, then using a relationship here, we can find what L is, and that turns out to be 300 yards as well. In other words, the region is going to be a square. We'll take the second derivative, which gives us -2. That's less than 0. So again, by this second derivative test, that tells us we have found a maximum. Example 3. You're given 1,200 yards of fencing material and wish to enclose a rectangular area. That sounds like example 2, does it not? Read on. Your property is bordered on one side by a river. Here's the schematic of what we're talking about. Hence, you only need to enclose 3 sides, this side, and this side. What dimensions must the rectangle have in order that the enclosed area be maximum? So again, area of a rectangle is length times width. The perimeter is 1,200 yards, okay? So now what we need to do is find a a relationship between L and W and the 1200. Now, before, remember, it was 2 L's plus 2 W's because we fenced in this side, this side, this side, and this side. This time, we're not going to fence in but these 3 sides. So our relationship is going to be L plus 2W. That's the fence we're going to use, and it has to add up to 1200. Now we're going to solve for either L or W. Now you have a choice, but let's make an intelligent choice. We're going to solve for L, which is 1200 minus 2W. You could solve for W, but you're going to have a fraction. It's not going to be a major problem, but I think we'll be better off avoiding a fraction if we can, and so we do, but that's your choice. So now what we do is we replace L in a determined equation with 12 minus 2W times W. Again, we're not going to use the product rule. We'll multiply this out, and like so, we'll take the derivative and we get this, and then we'll set it equal to 0, and we find that W is 300 yards. Now we need to find L. Well, L is 1200 minus 2 times 300, and that's going to give me 600. So L is 600. So this time we do not have a square. We do not have a square. We have a rectangle that's 600 by 300 yards. We take the second derivative, and that's -4. Again, less than 0 tells us we have a maximum. Now, the reason we chose 1200 yards in example 2 and in example 3 is so you would not assume that the difference in the answers was somehow related to the fencing. That has nothing to do, although if you did have a different amount of fence, obviously it would affect the problem. But keeping those two the same, we realize it has to do with the parameters and the constraints that we're given for this particular problems. Okay. Let's look at example 4. Example 4, you're given 1,200 yards of fencing material and wish to enclose a rectangular area to form a dog kennel. Again, sounds like example 2. However, let's read on. The fenced-in area will have 5 runways in order to separate the dogs. In other words, we're going to put fence across this way so that we have these individual runways within the kennel to put individual dogs. Note, the runways are not necessarily of equal width. They don't have to be. They can be. I think if you had your own kennel and you were serving a lot of different customers and you wanted to be able to not turn people away and you want to get the maximum number of dogs in or whatever, I think this is something you might do. Like big dogs go there, and obviously very small dogs would go there, would be your thinking. At any rate, again, our general equation is L times W. Now that's been our general equation in example 2, example 3, and now in example 4. But now let's find our relationship to the 1,200 yards. Well, the relationship is this. We're going to have an L and an L. We have 2 L's, 2 lengths. And we're going to have a width here, another one here, 2, 3, 4, 5. We're having 6 W's. So this is my relationship. 2L plus 6 W's is 1,200 yards. Now you might say, I thought it would be 5W. No, count them. Think back to when we just had a rectangle. A rectangle was just one big region. How many W's did we have? We had one region, we had 2 W's. The number of W's will always be one more than the number of regions. So this makes sense that we have 5 divided plots inside, and so it would be 6 W's. That's for your information. Now, since 2 goes into 2, 6, and 1200. Let's go ahead and simplify. You don't have to, but we like to do that. And so this is what we have done. And then again, what letter would you solve for? We're solving for L. Why? Because if you solve for W, you're going to have a 1/3 L. Again, it can be done, but let's not go looking for trouble. So I think this would probably be a wise decision to solve for L. So now what we'll do is, in place of this L in our formula, 600 minus 3W times W. Not going to use the product rule again. We'll multiply this out. This gives us this. We'll take the derivative. That's 600 minus 6W, set it equal to 0. So W is 100 yards. So L will be 600 minus 3 times 100, which gives us 300 yards for our length. We'll take the second derivative. That's -6. Again, less than 0. Therefore, by the second derivative test, it's a maximum. So there is our answer. Now, these feel like 3 good problems. They are not really high-level problems. They certainly are harder, more thinking than in the first problem, first example. But they're designed to give you a level of comfort in working problems. Okay, so they have a lot in common, but enough in difference to make the problem interesting. Of course, they all had the same 2 things in common. A was L times W, and the amount of fencing was 1,200 yards. So there was a lot in common, but different ways of looking at the same situation. Let's go to example 5. You wish to construct a wooden toy box with a square base and no top. In other words, our box is not going to have a top. And it's to have a volume of 500 cubic feet. That's volume. Of course, it's going to be made out of wood. Wood has thickness, but we're discounting the thickness of the wood. We're assuming that it's a very thin type of wood, and we're not going to get involved with the thickness of the wood because it will detract from the problem, especially at this entry level. So we make that note for you. Question is, what dimensions of the box will use the minimal amount of material? Up to now, we've had problems looking for the maximum, largest, and now we're looking for the smallest. Now, before we write our equation, let's take into consideration what is volume. Length times width times height. So that's what we have for our box. Length times the height of the box, the width of the box, and the length of the box, if you will, or depth. Now, we've said that we're making L equal W. Why? Because we're told that the base is square. So these have got to have the same letter. So let's just make this W and call this W, okay? That dimension. So that means that our volume, which was length times width times height, is now W squared times height, or W squared times H, okay? So that's what the equation for the volume of the box is. We're told, however, that the volume is 500 cubic feet. So let's, in the place of V, put 500. And now let's solve for either W or H. We're choosing to solve for H. Why? Because H is 500 over W squared. If you solve for W, you're going to have a radical. It can be dealt with, but we're not going to make that choice for us. But if you want to ever explore any of these problems, walk through that alternate way, do and see what it does to the problem. It should not make it impossible. It just will make it maybe a little more complicated, but we haven't tried working it that way, and we are not here on this particular lesson going this route because we think it's a preferred route. Now, how much material do you need? In other words, that's what dimensions of the box will use the minimal amount of material. Remember, that's the first thing you have to do is decide what is it you're trying to maximize or minimize. And we could have written this equation first and then come back to do this. We kind of just juxtaposition the order here. It doesn't matter. The material equation would be this. We have a bottom. That's W by W is the amount of, it's W squared. Okay, that's the area of the bottom. Each side is H times W, and we have 4 sides. So this is the amount of material, 4 sides and a bottom. There is a version of this problem where you have a top, and it's written the same way, except instead of W squared, you would have 2W squared if you had a top and bottom, but we do not in this particular problem. So we have M is 4HW plus W squared, and we found here that H is 500 over W squared. So what we're going to do is in the place of H, we're going to put 500 over W squared times W and plus W squared. So now we have one unknown, that's simply W. Let's go ahead and multiply before we take derivative. 4 times 5,000 is 2,000, and W times 1 over W squared is going to leave us just a W in the denominator and W squared. Now we'll take the derivative of this. Now remember, this is 2,000 W to the negative 1, which makes it, when we take the derivative of W to the negative 1, it's going to be minus 2,000 W to the negative 2, or negative 2,000 over W squared. When we take the derivative of W squared, we get 2W. We'll set it equal to 0. Okay? Now, let's simplify by multiplying everything by W squared. So when we multiply this term by W squared, we have just negative 2,000. When we multiply this term by W squared, we get 2W cubed. When we multiply 0 times W squared, we get 0. Okay? Now, let's see if we can solve for W to find our critical numbers. So what we'll do is we will simply bring this over, which will make it a positive when we bring the 2 and divide by 2. So we have W cubed is 1,000. We're not showing every step in these problems. Just follow along, or if you're having trouble keeping up, stop the frame and look at it, make sure it makes sense to you. And then we want to find W. That's going to be the cube root of 1,000. Well, it turns out nicely that since 10 times 10 is 100 times 10 is 1,000, W is 10 feet. And now we need to find out what H is. So in the place of W, we're going to put 10 squared. It's going to give me 100. And when we divide that into 500, we're going to get it 5 feet for H. So they are the dimensions. W is 10. So it's going to be 10 by 10 by 5. If you wonder if this is indeed a minimum, then we have to go up here to the our first derivative and take the second derivative, and this is what you get when you take the second derivative. And we don't have to put numbers in. 4,000 is positive. W squared is always positive. So we have a positive over a positive. That's a positive plus 2, which is a positive. So this quantity we know is positive, that is greater than 0. So by the second derivative test, we declare it's a minimum. Okay. A little harder problem. Now, example 6. You're constructing a rectangular window with a semicircle window on top. Now, a semicircle is a half a circle. So what we have here is we have a window with a bit of glass, and this part is rectangular, and a semicircle part is on top. The perimeter of this window is 28 feet. That means the distance from here to here to here and around here is 28 feet. We want to find the dimensions of the window that allow the greatest amount of light to enter. Now, that's kind of a coded message to tell you they want the maximum area. The greater the area of the window, the more light that's coming through. I think that's hopefully clear. So we've labeled the sides. This we're calling Y. This we're calling, this is the radius of the circle, okay? Radius of the circle from here to here, here to here. This, we're going to call it X. And if we call this X, this part X, then this part is 2X. So this, we're making 2X. Now we could have called this X and made this 1/2 X. And I'm not sure which would be better in this case. But anyway, this is a trick that you can use to somewhat cut down on fractions. And so that's what we've decided to do with this problem. This is Y is the length, the width is 2X. And so that makes the radius of the semicircle X. Now, the area of the rectangle, since from this drawing would be length times width, which is 2X times Y. That's length times width. The area of the circle, remember a circle is pi r squared, so the area of this circle is pi x squared, but that's for the circle. We have a semicircle, so that area is 1/2 pi x squared. So that is what we have. Now, what we're interested in, we're interested in maximizing the entire area. And that means the entire area is made up of this part, the rectangle, which is 2xy, plus the area of the semicircle, which is 1/2 pi x squared. Now, again, we have 2 letters. Is there any way we can reduce this to 1 letter? Well, we haven't used this information yet, and that is the perimeter is equal to 28 feet. Now, what is the perimeter? Well, we have 2x, okay, plus 2y, okay, and then we have, I'm sorry, 2y, because we got a y and a y. I'm sorry, it's 2x plus y, which is 2x plus 2y. That's what we have here. Now, remember, the perimeter of the circle is the circumference. Now, the circumference is pi times the diameter of the circle. So since this is 2x, that's the diameter of the circle is 2x, or 2 pi r, which is another way of looking at circumference if you're dealing with radius. And in other words, so it's 2 pi x. That is the circumference of the circle, but we have a semicircle, so it's not going to be 2 pi x, it's going to be pi x. So that's the perimeter of the circle, okay? And since that's the perimeter and it's equal to 28, we'll set it equal to 28. Now, I think you would want to solve for y rather than x. I think if you look at this, to solve for x, we're going to have to factor out an x, and I think we'll be better off solving for y. But before we do, you see you have a 2x, and you have a 2y, and you have a 28. We're going to divide everything by 2, okay, and bring it so that y is isolated. I'm doing 2 steps in one. In other words, I'm going to divide everything by 2. So that's going to make, when I do, that's going to give me just an x, okay? And when this is going to be 14. Half of 28 is 14. Let's zero in on that. That stays where it is. Half of this is going to be x, and when we bring it over, it becomes minus x. This will be y, and it's going to stay here. And then this is going to be 1/2 pi x, and when we bring it over, it's negative. I hope you followed that okay. We're just aren't showing every step here, and I'm working along with you as you look at this. So we're isolating y, which means everything that doesn't have a y is going to be brought over to the right. Maybe I should have said that outset, and then we'll just take half of everything. That is what you will get. That is your y. Now, what are we going to do with that y? Well, what we're going to do, this is my equation up here. So what I'm going to do is I'm going to substitute in a place. See, I only have one y in my area formula. I'm going to put this in for y right there. So that's what I have. Now what I'm going to do is simply multiply everything by 2x. And this is what I get when I multiply everything, every term by 2x. Plus I still have this term here hooked onto the end, okay? And now what I'm going to do with this is I'm going to combine terms where I can to kind of simplify this, and we have it looking like this, okay? So kind of dressed it up a little bit there, not a lot, but a little bit. Now I'm going to take the derivative of this, and when I do, I get 28, okay? And I get a minus 4x, and then I have a 2 times, and the 2's cancel, gives me a minus pi x. So that's the derivative. Now I set this equal to 0, and I want to solve. Well, what I'm going to do is I'm going to bring this 28 over, and I'm left with a minus 4x and a minus pi x. I'm going to factor out a negative x, and I'll divide by this, and then I want positive x, so I'll multiply by -1 each side of the equation, and I get x is 28 over 4 plus pi. A lot of math is going on there. I hope you can follow that. Okay, if not, listen, run through it again. This is a much more involved problem than the previous problems, okay? Now, so that's what x is equal to. Now we've got to figure out what y is equal to. So y is equal to 14 minus x minus 1/2 pi x, okay? And when we do that, we find that y turns out to be 28 over 4 plus pi as well, okay? Now, we're almost through with this problem. Before we go any further, let's take the second derivative. When I take the second derivative, I get minus 4 minus pi. Minus 4 minus pi is always negative. That tells me my answer is maximum. So we've got that out of the way. Now we have one last thing to do. It asks you for the dimensions. We do know what the y dimension is, but we don't really have the x dimension. We have that x is 28 over 4 pi. And this dimension, the width, is twice that. So we've got to double that. Double 28 over 4 plus pi. When we do, we get 56 over 4 plus pi, and they are my dimensions. Of course, this is the x for the radius there too. So we've got this problem pretty much worked out. It's a lot involved in this problem, a lot to follow. We're using area of a circle, semicircle, circumference, area of a rectangle. We're using a lot of things in this, and we've limited by not showing every step, what may not be bring comfort to you, but we have such a limited space to work on here on a problem like this to get it on the screen that we're not showing every step. But you might freeze it, make sure that you follow and it makes sense to you, and that will be a good thing to do. Okay. Now, I think this is our last problem. This is example 7. An individual is in a rowboat 4 miles from the shore. Okay, so here we have the boat 4 miles from the shore. Okay, this is shore, right here. A diner is located 6 miles down the beach from the point on the beach closest to the boat. Well, this is the point on the beach closest to the boat. So this is 6 miles. Here's our diner here. Now there's a person in the boat, and they can row the boat at 2 miles per hour. So they can row at 2 miles per hour, and they can walk along the beach at a rate of 3 miles per hour. Now, we want to find at which point they're going to row to the beach to a certain point, get out of the boat, and then walk to the diner. And the question is, to what point on the beach should they row to and then walk so that they can get to the diner in the least amount of time? Interesting question. And before I begin this problem, let's think about some things. Suppose they rode at 3 miles per hour and walked at 2 miles per hour. Well, if they could row faster than they could walk, it would make sense to just row the entire distance, right? Because the shortest distance is this line right there. Straight line, shortest distance between 2 points. But because they're very closely matched here, it works out that they will not get that fast just by rowing the whole way. So they're going to row a little bit, and then they're going to walk the rest of the way. So this is what we're interested in. We're labeling this as X. This right here is X. And what we need to find out is, so this is 6 minus X. You see, this is 6 miles, and this is X. So if this is 6 and this is X, then this distance is 6 minus X. That's how far they're going to walk, 6 minus X miles. They're going to row this distance. Now, what is this distance? Well, we've got to find out what this distance is. This is 4, and this is X. So, and this is a right triangle here, okay? And what we've got is, this is the hypotenuse of a right triangle. So 4 squared, which is 16, plus X squared, added together, gives you this distance squared, but we want this distance. So it's the square root of 16 plus X squared. So this distance is the square root of 16 plus X squared. This distance is 6 minus X. Now, what is it we want to minimize? Time. Well, rate times time is distance. Think about it. If you go 50 miles per hour, that's your rate. For 2 hours, that's your time. How far do you go? 100 miles. Rate times time is distance. So time is distance divided by rate. So the distance they're going to row is square root of 16 plus X squared. The rate at which they row is 2 miles per hour. The distance they're going to walk is 6 minus X miles. And the rate at which they're going to walk is 3 miles per hour. So this is the time rowing, and this is the time walking. So the total time is the time rowing plus the time walking, which will be this quantity plus this quantity, okay? So we've written that like so. We need to take the derivative. Well, remember, this is 16 plus X squared to the 1/2 power. And so when we take the derivative, we'll get 1/2. This quantity to the negative 1/2 times the 2X inside. Anyway, we've done that for you here. You can check us out. That's the derivative of this. The derivative of this is pretty obviously that it's 1/3, because what you've got, if you break this up into 6/3 and minus X/3, this 6/3 is 2, whose derivative is 0, and minus 1/3 X derivative is minus 1/3. So that gives us this. Now, what we're going to do is we're going to set this equal to 0 to find our critical numbers. We'll bring the 1/3 over, which is what we've done here. Now, this radical bothers us. So what we're going to do, it's a square root. So what we're going to do right here between this step and this step, we're going to square each side of the equation. And when we do, we get X squared over 2 squared, which is 4, and the square root squared lifts the radical, and this gives us 1/9. Okay, now what we're going to do is cross multiply, and that's going to give me 9X squared is 4 times 16 plus x squared, okay? Which is 64 plus 4x squared, okay? So we've multiplied this, but we've also, when we got over here to cut out a step, this is going to be 4 times 16 plus x squared, which is 64 plus x squared. And now what we'll do is bring the 4x squared over. That gives me 5x squared, and then divide by 5. So that gives me x squared is 64 over 5. So x is the square root of 64 over 5, which is 8 over 5 miles down, square root of 5 miles down shore. 8 over the square root of 5 miles down shore. And so we have found the x. Now, you'll have to forgive us, but we're not going to take your time to take the derivative, the second derivative, to verify that this is a min, because it's not a really hard thing to do, but probably not worth the time. This has been a rather long lesson to start with, and we assure you that it is does check out to be a positive. The second derivative does, which means that we did find this is the minimum time. So that completes that problem, which also brings us to the end of this particular lesson. Now, keep in mind, we started you out with a problem that you can do in your head, just to give you a feeling of the order. Then we took a problem that was identical in terms of the amount of fencing and the equation, which was area, length times width. So we had 3 problems that we basically worked over and over again 3 times. That's a good problem for you to be aware of. And then we came to the 5th problem about the box, and that is somewhat more difficult, but certainly would be called middle of the road as far as level of difficulty. And then the last 2 problems are quite interesting and certainly not impossible, okay? But they are a lot more involved than the earlier ones. If you go to any textbook, calculus textbook, and look at the section on optimization or max min word problems, you'll find that they have quite a few problems of every type. And we're not here to work every problem of every type. All we wanted to do is acquaint you with the technique used. And so hopefully you may parts of this lesson or all of this lesson view again, and as often as you need to, till you feel like you can take ownership of this topic. This concludes this particular lesson.